All right, so let's get started. This is going to be a virtual lecture to make up for us missing class on Friday. It's sort of a perfect lecture to make up because there's not a lot of in-depth examples that we're going to do in this. It is important to watch and listen to, though, especially as we delve into the land of deflections for beams and frames. Now, we have already computed deflections for trusses, and we utilize the method of virtual work. We're going to continue to use the method of virtual work for beams and frames. It's just going to be tweaked a little bit because we're dealing with moments as opposed to axial forces, and so that's going to change not only how we deal with deflection in general, but it's also going to change the section properties that we use. We're not going to use the area. We're going to use something else. So we need to take a step back and understand the differential equation for beam deflection. One of the other things that we need to handle is how we deal with unit conversions. We did have to do unit conversions with truss deflections. We have to do them with beams as well. But because the units are a little bit more involved, we're going to derive some conversion factors. So the magic numbers that we're going to derive are going to be for deflections. We're going to derive a number called, and it's going to be 1728. And we're going to understand why 1728 is sort of our magic number. And then for for slopes, or for slopes and rotations, we're going to derive 144. But typically what I like to do is I like to convert to degrees, so we're going to have 180 over pi. So that's going to be sort of one goal in this lecture, is where do those conversion factors come from, and that'll become clear as we move on, or move into this. Okay, so the first thing I want to do is I want to set the stage, and I want to talk about virtual work for truss displacements. So if we have a truss, remember to compute the displacement of a truss, and I want to make sure that I'm indicating that we are using typical USCS units. The formula that we use is this formula right here. We sum up the little f, big FL over EA for all of our members. And so we're basically summing up that internal energy. First off, we have two analyses that we perform. We have a real analysis and we have a virtual analysis. The results of the real analysis are in kips, and then the results of the virtual analysis are unitless. They come from placing a single load on the structure. We place a load of 1 at the place that we're interested in computing deflections in the assumed direction of that displacement. So remember, if we assume a direction and we get a positive answer, it means our assumption is correct. If we get a negative answer, we just flip the direction. Okay. The length of the member needs to be expressed in inches, and so typically truss dimensions are expressed in feet, and so this is where the unit conversion factor comes from. You could argue that the deflection conversion factor for trusses is 12, because you're multiplying your truss lengths by 12. So in this case, you're sort of multiplying all of these by 12. So we're going to come up with similar unit conversion factors for beams and frames, but they're not going to be 12. They're going to be, as you saw in the earlier slide, 1728 and 144 times 180 over pi. But we'll get to that here in a bit. We finally have a Young's modulus, or an elastic modulus for each member, and then the cross-sectional area for each member. And so this is how we compute truss displacements using the method of virtual work. We're going to find that the method is very similar for beams, just with some slight tweaks. Okay, so to be clear, let's remember where these came from. Okay, where this method came from. So where it came from was summing up both the external work that was done to the system, as well as the stored energy, the stored strain energy that it stores as a result of those loads being placed on it. I used the example of Link drawing the bow. He displaces the bow, or the bow undergoes some deformation, but then the bow stores energy as a result. So if you set the energies equal to one another, the external work being done and the stored energy, you can compute the deflection. We also, the reason that we did a virtual analysis is because we needed a means of computing the energy where we're interested in finding the deflection. So we preload the structure. So we start off with that fake load P1, and then we add our real loads to the structure, P2. And then we found, based on all the algebra, that it made sense if we just set P1 equal to 1. That's where that unit load comes from. But we ultimately got kind of crafty, and we set U2 equal to W2, because those were the simplest regions geometrically. We were dealing with rectangles, not triangles. And then they also, if we set those energy components equal to one another, it ultimately gives us everything that we're after. The real deflection, delta 2, equals a pile of junk. Now keep in mind, delta 2 is multiplied by this P1, but again, that's why we set P1 equal to 1. Now I want to take a step back just to make sure that I'm going to make a point about something that did not affect trusses in the slightest, but it's definitely going to affect beams and frames, and that's a note on constant versus variable forces. Okay, so if we're talking about a truss element, so if we're talking about, let's say some truss member or some truss, and, we have some loads on it or some loads on it, what have you, and we compute our loads and go through our math and whatnot, let's say that we find that that member in the truss is experiencing 20 kips in tension, okay? And I'm talking about this member right here. What that means is that that member is experiencing 20 kips everywhere along its length. So it's 20 kips in tension, and it's 20 kips everywhere. It's 20 kips here, 20 kips here, 20 kips here, 20 kips here. It is experiencing a constant force along its length. That axial force of 20 kips does not change, because that goes into the assumptions that we use when we analyze trusses in general. Remember, when we analyze a plane truss, we assume frictionless joints. We assume that the loads are applied directly at the joints. We assume that the centroids of the members coincide. What that means is that the members are only carrying compression and tension, and it's constant throughout their member length. Okay, but I want to ask the question: what would happen if the load did change? What if we went from 20 kips to 30 kips? What if we had a variable force along the length of the member? Okay. Keep in mind, this little formula up here, that only works if the F values are constant. What if they vary? And either one of them could vary. Whether or not it's the little f or the big F, it wouldn't matter. This is going to apply. So, again, the key word back on this previous slide is that we are summing up the energy. Okay? And summing up the energy should bring up a mathematical concept of integration, because that's what an integral is. Remember, an integral is just a representation of the Riemann sum. You're slicing up those individual elements and then adding them up. That's basically all an integral really is. So the idea is to sum up the little bits of displacements and the little bits of energy in each differential element and just add them up. So how would that work? Well, the way that we did that for axially loaded members is we said, okay, the stress and the strain are linearly proportional through Young's modulus. That's this one right here. But what about the axial loads? Well, instead of sigma being F over A, what if it's F of X over A? What if that force varies? Instead of the strain being constant, we now have a rate of strain. We now have the derivative of displacement with respect to X. So now we can combine those, rewrite them a little bit, rearrange in order to get a displacement along each element. So the differential displacement is F over EA dx. Multiply that by the little f, and then integrate. And so what we're getting is, instead of the u being a constant up here, u was just little f, u2 was little f, big F, L over EA. Now we have u2 being little f, big F over EA, but now we're integrating from 0 to L. Now, does this formula work if they happen to be constant? Well, what happens if they happen to be constant? So Calc 1 taught me that I can pull out anything that's a constant. So I have little f, big F over EA times the integral of dx. The integral of dx is x, evaluated from 0 to L. So that's just L. So that goes back to our original definition. So I guess the way of thinking about it is what's going on here on this slide. Here, I'll just erase it this way. Is that this slide is generalizing our expression for internal storage strain energy if the forces are variable. So instead of little f, big F times L over EA, and it's just a constant, we have little f, big F over EA, and we're integrating that from 0 to L. So think the L goes away, and instead of an L, I'm just integrating. Okay, and that's going to be important because that's what we're going to see with beams. So let's talk about beams. Okay, now the first thing that I want to make sure that we're covering is the differential equation for the deflection of a beam. This is the general mathematical principle that defines how beams behave, because we need to understand that to understand how virtual work is specifically going to change for beams and frames. So I want to take some steps back and make sure that we're clear on some very basic math preliminaries. So let's start off with a very quick review of section properties. And all section property is a numerical measure that characterizes a bounded area. So for example, let's say I've got the curve f of x bound by the x-axis between points A and B. By now, it should be pretty clear that if I integrate that term or that function from A to B, I am computing the area under the curve. Now, I tend to use a little bit of shorthand, and what I will do is I will say instead of f of x dx, I will write dA. So the idea is that, this is, dA right here. And so dA is just the width times the height, or rearranged f of x dx, and I'm just summing those up over the region. So that's how I go from this to this. That's just my shorthand way of writing that. I'm kind of lazy sometimes, but I also think the shorthand makes it a little easier to understand. Okay, now what we have here is an integral defining area. What I want to take a little bit of time to do is define integrals that represent moments of area. So if I have the integral of dA being the area, the integral of x dA or the integral of y dA are what are called moments of area. Now specifically we call them first moments because we have second moments, which would be the integrals of x squared or the integral of y squared. Now note that the symbols are flipped. That's not a typo. That's correct. For example, the integral of y dA is the moment about the x-axis. So kind of the explanation for that is if this is the x-axis and this is the y-axis, and I'm talking about some region, and I'm talking about some point of interest, the distance from the x-axis, how far is it from the x-axis, is y. That's what that is. Similarly, the distance from the y-axis is x. So that's why the symbols are flipped, and that's not a typo. That's accurate there. So the first moment of area, textbooks tend to use the letter Q to represent that, but the second moment of area, we tend to use the letter I because second moments of area have a very special name. We call those the moments of inertia. By now, you should have seen those in either Engineering 216 or 213. I know I cover them in both of those courses to make sure that you've seen them. But the moment of inertia is an incredibly important section property for a shape because it, as I said in 216, it is a measure of a beam's resistance to flexural bending. It is a measure of flexural stiffness. And we saw that in 216. We're going to see it in here as well. Okay, so the last thing I want to talk about is curvature. So let's say I have some given function f of x. So one thing that you should be very familiar with is computing the slope of that function. Now, if I give you a function to compute the slope, you take the derivative of that function. The concavity of a function is computed using the second derivative. And I think that most engineering students are pretty familiar with the slope and the concavity based on the first derivative and second derivative tests that you learn about in Math 229 or Calc 1. However, if I asked you, okay, here's the slope, here's the concavity, how do you compute the curvature of a function? I imagine that one's probably not one that you remember. If you still have your textbook, dig it out, go through the index. It's in there, I promise. It might have been covered by your calculus professor. It might not. It's something that usually you kind of gloss over a little bit. But the curvature of a function has a very specific definition in mathematics, and it's computed as follows. We take the second derivative divided by the following quantity raised to the 3/2, and it's 1 plus the first derivative squared. I'm calling the Greek letter kappa as the curvature of a function. I could invert that, and that I would call that the radius of curvature. And so you're going to see curvature show up here in a little bit. The fundamental DiffEq, the fundamental differential equation that defines beam deflection, we sometimes call the moment curvature equation, and this is sort of why. Okay, now let's get into beam deflection. Okay, so like with trusses and other instances, we've made some assumptions to make the analysis a little more doable. We're going to make the same assumptions for beam deflection. We're going to make the same types of assumptions. They are different assumptions because the mechanics for beams and frames are not the same. We're talking about bending versus axial deformation. So we need to make sure that we're clear on this. First off, we are assuming linear elastic behavior, which is very common in structural analysis procedures. Again, you really don't start handling nonlinear analysis until you get into some pretty advanced stuff as a structural engineer. Deflections are considered small when compared to the original member lengths, and so what that means is that, and we make those same assumptions when we analyze trusses, is that when you take load and you put it on a structure, it deforms. Basically, what that assumption means is that we do not have to check equilibrium again on the deformed shape. It's not, in other words, we have the structure, it deforms. We don't have to recompute reactions or reanalyze the structure. We don't need to do that. There are some instances where engineers do have to handle that. It's what's called a second order analysis. You'll find that a lot in tall building design under wind and earthquake and things like that, where earthquakes where you have to consider second order effects. We're not really going to worry about that for this, and that's sort of an advanced structural analysis topic as well. When we're just getting into it, we're going to keep things simple. So if we look at the deflected portion of a beam, let's say it looks something like this, and I'm zooming into a really small portion, and so you'll notice I'm kind of assuming that it is sort of a circular deformed shape. Again, I'm trying to use the simplest geometry that I can, and under zooming into those small differential elements, that's a pretty reasonable assumption. So let's look at these geometries here. So the first thing I want to express is the length initial. Okay, and what the length initial means is let me go back. What the length initial means is I'm talking about, let me use a different color here. Let's use blue. Okay, so I'm talking about this length right here, okay? And where I get this formula comes from some really basic geometry that says that if I have a angle here and a radius here, and I want to determine the arc length is r times theta. And so what I'm basically saying is that the initial length of the beam before it deforms is the radius of curvature, rho, there's that radius of curvature popping up, times theta, okay? So that's the initial length, and I can take that as the initial length before deformation, okay? Everywhere else along the length, the depth of the beam, the length changes, okay? So in other words, this dashed line right here, this one that I'm coloring in here in blue, has a different length than the unstretched portion. So there's an undeformed and a deformed. The undeformed is just the angle times the new radius. And instead of rho, the new radius is rho minus however far away you are from the neutral axis or from the centroid. Okay, so this is just taking that and chugging out the algebra a little bit, distributing that. And so now I have a final length and an initial length. And if I have a final and an initial length, I can define stress and strain, or I can define strain as the change in length over the original length. So the change in length being L final minus L initial divided by the original length, L initial. And so you'll see that the radii of curvature all cancel out, and I'm left with negative y over rho, so that's the strain, and then the stress is just E times the strain. So there's my my definition of stress from a compatibility standpoint, looking at the deformation of the structure. Now I want to look at stress on the other end. I want to look at it from the equilibrium side and see if I can set the two terms equal to one another. Okay, so let's look at moment in the cross section. So if I look at the beam and I say, okay, let's take a little slice of the beam. Let's just take a small little slice right here, and let's just assume for simplicity that the beam is three-dimensional. So there's the neutral axis right there. There's my little bit of a slice that I'm taking out. Okay, let's see if we can simplify this a little bit. So if I want to determine the total moment in the cross section, what I want is this force in that element, and so that element has an area and it's being multiplied by some stress. Okay, so there's the force, and then the distance from the neutral axis, this distance right here, that distance right there is going to be some distance y, whatever that is. And then so if I take sigma times y times the area and then integrate that, there's the moment, right? Because I have force times moment arm for that little bit, and then I'm just summing it up for all the little bits along the cross section. Okay, now you'll notice there's a negative in there. The negative results from the sign convention that we use as structural engineers, where we have sort of smiley face positive for bending moments. So if you're wondering where the negative came in, that's where that came in. Now I have this integral right here. I've got this stress term in there. I'm going to take that stress term, I'm going to plug in what I had before on the previous slide, and then I get this. Now I've got E over the radius of curvature times this integral of y squared dA. But the integral of y squared dA, that's the moment of inertia. Okay, so I can make this real simple real quick. Okay, the only thing left to do is to see what the heck is going on with rho. What the heck is going on with the moment of inertia? So this is me just sort of rewriting things a little bit. So I have the moment is EI over rho, or just putting the rho on one side and M over EI on the other, just taking care of the algebra, I get this. Now let's look at our curvature expression. Remember, we're using small deflection theory. So if we look at our curvature expression, small deflections indicates really small slopes. And if I take a small slope and I square it, I get a really, really, really small slope. So what I'm doing right here is I'm basically saying I've got, go back here. So what I'm saying here is I've got V prime over 1 plus V prime squared, all raised to the 3 halves. So maybe I'll just do it like this. Okay, but V prime is a really small number, and if I square it, I get a really, really, really small number. So we're just going to set that equal to 0, and 1 raised to any power is 1. So I'm just going to say that the curvature is basically equal to the concavity, so the second derivative. And so with that, I can take that kappa term and replace it with the second derivative, and I am left with one of the most fundamental equations in all mechanics, the moment curvature equation, or Euler-Bernoulli beam bending, which basically says that the second derivative of deflection is m over EI. It's one of the most fundamental equations in all mechanics. So how do we use it? Well, let's put this into the land of virtual work. How does virtual work change for beams? Well, in the land of virtual work, we always analyze 2 structures. We have the original structure with all the loads present, and then we have the virtual structure, which has a single unit load at the point of interest. So what we do for external work is, if we're interested in computing displacement, we just place a unit load on the structure. But if we're interested in determining rotation, we place a unit moment at the point of interest. So now you can see where concentrated moments are starting to become a not just something that you need to understand from the real world standpoint. If you have a cantilever beam, it's going to have a moment reaction and what have you. Or if you have an element framed into a beam that's being twisted, you're going to have a concentrated moment. But now concentrated moments are becoming an analytical tool. We have to be able to handle them because we're actually using them to compute rotations. So if we're interested in computing deflections, place a unit load. If we're interested in placing rotations, place a unit moment. And just a heads up, I'm going to use the term slope and rotation interchangeably. They basically mean the same thing. If we're looking at a beam and we want to know how much an element rotates or what the slope is, those are the same thing. Same thing where displacement and deformation kind of using somewhat interchangeably. Just like with truss deflections, we assume a direction. If we get a positive answer, it means our assumption is correct. So that's basically all that means. Now, what we've got to do and what really makes beams different is that we have to integrate our energy. Now, if we go back to our differential equation, the differential equation for deflection says that the second derivative of deflection is m over EI, but that also means that the first derivative of slope is m over EI, because slope is just the first derivative of deflection. The reason that we have to integrate is because moment changes as a function of x. I don't think we've ever seen a moment diagram that looks perfectly flat. It doesn't mean it doesn't happen. There actually is a case where you can have regions of constant moment, but most of our moment diagrams go up and down, and they're curved, and they're linear, and all sorts of different things. So the moment changes, and if the moment changes, we're going to have to integrate to determine that stored strain energy. We're still only going to focus on U2, so it's going to make our life a little easier there. But what we're going to do is we're going to find the amount of rotation that each element goes through, and then just integrate, just like we did with trusses. We find the amount of deflection that each element goes through, and we integrate. So what do we got? Well, I'm taking this expression right here and just solving for d theta. So I'm just multiplying both sides by dx. So m over EI times dx. Multiply by the virtual component. This is the same thing we saw in the very beginning of the slide, only instead of a little f and a big F, we're dealing with a little m and a big M. And then integrate. That's basically it. Set the two energies equal to one another. We set that virtual load equal to 1. And by golly gosh gee, this is what we get. Okay? So for virtual work for beam deflections, this is how we compute the deflection in a beam. Okay? So we have real moment functions and we have virtual moment functions. So if you remember, we had an assignment where we had to compute moment functions and then plot the beam deflection, or the shear and moment diagrams in Excel. This skill is going to start to become really, really important when we compute deflections, because we're going to need those moment functions and we're going to need to integrate them. So we're going to have a set of moment functions for the real loads and a set of moment functions for the virtual loads. And I say set because they're dependent upon the type of loading. You could have multiple of either, and so you need to be able to handle those adequately. And we're going to have several examples, and really our examples are focused on just that, on how to ensure that you're dealing with however many real and virtual moment functions that you have. That's really the main challenge. Again, the little m the big M come from the real loads, the original loads on the beam or the frame, and then the little m comes from taking all those loads off, putting a single unit load at the point of interest with a magnitude of 1 in the assumed direction of the deflection. Now, E is your Young's modulus in KSI. I is now showing up. It's the moment of inertia in inches to the fourth. And again, this is what I was saying earlier. If we have multiple functions, we're going to have multiple integrals, but we're going to see how we can deal. The actual integral part is really easy. We'll be able to use some tools to make our lives a little easier on that. The hard part is, or the last thing that we have to talk about, and this isn't really the hard part, the last thing that we need to talk about are units. Okay, look at what's going on here. This is using typical US units. We have moments in foot kips, but we have E in KSI and I in inches to the fourth. What is going on with the units? Okay, so let's take a look at the differential equation for deflection. Okay, so the second derivative is m over EI. Okay, now if I integrate that, okay, from a unit standpoint, that's going to yield one more length unit in our answer. And what I mean by that is this. So if you have some function that's like, I don't know, let's just say 3x squared plus 7. I don't know. Okay, and you integrate that, what you're going to get is you're going to get something like x to the third plus 7x plus c. Okay, so what that means is if this highest term has an order of 2, like x squared, the highest order term here has an order of 3. Now, in the land of structural analysis and moment functions, what we're talking about is adding another length unit, right? If you take a shear function and you integrate it, you get a moment function. Shear is measured in kips. Moment is measured in foot kips. So imagine what happens if you integrate again or integrate again. It's just adding another length term. I'm not saying every time that you integrate m or integrate a moment function is just m times l. I'm just saying you get another length unit as a result. So slopes, if we just look at it from a units perspective, are going to be moments times lengths over EI. And then deflections are going to be ML squared over EI. And again, this is just a dimensional analysis, just looking at units. Well, let's go back to our units that we're using for USCS system. So forces are in kips. Member lengths are in feet. So that means that distributed loads would be in kips per foot. Moments would be in foot kips. But modulus of elasticity, that's in KSI, and moments of inertia are in KSI. So let's carry that out. So with rotations, we would get ML over EI, so some term in foot kips times some term in feet divided by KSI times inches to the fourth. So the kips cancel, that's fine. But then if we track their units out, we'll get foot squared over inches squared. And then similarly with deflections, we'll get feet to the cubed, or feet to the third power over inches squared. So there's something mixed up on our unit system that's not right. And I think that's pretty apparent that something like this would happen if we look at the inputs. If the member lengths are in feet, but your material and section properties are in inches, something's got to give, okay? So we have a problem we need to deal with, and we need to ensure that our answers are usable, okay? Remember, we kind of had a conversion factor for trusses. Like, we didn't really call it a conversion factor. We just multiplied the lengths by 12, but that 12 was a conversion factor. We're going to have to derive a similar unit conversion factor for slopes and rotations. To get those usable factors, we need to ask is what are our desired units at the end of the day. And so typically for me, I like my slopes and rotations in degrees because slopes and rotations tend to be pretty small numbers. Your book might actually not do that. Sometimes your book might do them in degrees or might do them in millirads. We'll get into that when we start doing some examples. But for deflections, I think we all agree that the units need to be in inches. But for the sake of discussion, let's talk about degrees. Let's just say that we want our slopes and rotations in degrees. So what I'm going to do for the slopes is that if I have foot squared over inches squared, I'm going to need to convert two of those, or those inches, I'm going to have to convert them twice. So I have 12 inches per foot, 12 inches per foot, and then I'm doing that 180 over pi because that rotation would ultimately then be unitless, and I want it in degrees. So ultimately, I've got 144 times 180 over pi. And for displacements, I've got, that's what I've got here, is I've got, one more foot term, so I'm having to multiply 12 times 12 times 12. 12 times 12 is 144, times another 12 is 1728. So now you can see where that 1728 came from. So we have these pretty magic conversion factors that we derive. We have these pretty magic conversion factors that we derive for slopes and deflections. For slopes, 144 times 180 over pi, and then deflections, 1728. These might seem a little complicated right now, but what I'll tell you is that when we actually start getting into some problems computing these deformations, you'll find that if everything is in your standard USCS units from the get-go, which usually they are as a structural engineer, then just having these conversion factors on hand actually makes things a lot easier when you're doing these problems. And so the way that this is going to work is we're going to start in class dealing with problems that only have a single moment function, and then we'll get into problems that have multiple moment functions. And like I said, the real challenge with beam deflections is not the actual integration itself. That's easy. It's really not the math. The actual plug and chug calculations are pretty easy as well. The two challenges are how to deal with multiple moment functions and how to derive the moment functions themselves. If you can do that, the rest is cake. And so we will get into that when we return next week. And with that, that's all I have. You all have a wonderful weekend, and I will see you on Monday.